Welcome back to the deep dive. It is wonderful to have you with us again.
It is great to be here. I'm really, really looking forward to this one.
Usually when we sit down to do one of these, we have a very specific, almost a laser-focused target in mind.
Right.
We're looking at, say, the rise of a specific tech startup, or maybe a singular, really nuanced event in history. We tend to, drill down into one vertical shaft of knowledge.
We do. We usually go narrow and we go deep. That's kind of the format.
Exactly. But today is completely different. I was looking at the source material we have for this deep dive, this massive, comprehensive world encyclopedia, and I realized we aren't drilling a hole. We're trying to map the whole territory.
We are. We're attempting what you might call a theory of everything discussion. We aren't just looking at one gear in the machine. We're trying to look at the whole engine.
Theory of everything. I like that. Because when you flip through this source material, it's not just a collection of random facts. It feels like a narrative, doesn't it?
It really does.
It starts with the invisible rules of the universe, physics, atoms, gravity, and then it builds the stage those rules play out on, the Earth, the continents, the oceans, and then finally it populates that stage with life.
And not just life, but the struggle of life. That's what jumped out at me during my reading. You see how the laws of physics create a desert, and then you see how biology has to, twist and contort itself just to survive in that desert?
Yes.
It's a story of adaptation to physical laws.
It's really a journey of scale, isn't it? I mean, we are going to be talking about things as small as a single red blood cell and things as absolutely massive as the Pacific Ocean.
And the connection between them. Because they are connected. That's the key.
And the connection is us, or maybe more accurately, the human ability to observe them. That's the theme I really want to pull on today.
That's a great theme.
Because whether it's Isaac Newton watching an apple fall or a satellite mapping the Amazon rainforest, this entire encyclopedia is a testament to the human eye and all the tools we've built to help it see better.
That's a beautiful way to frame it. Science isn't just a book of answers. It's a method of observation. It's a way of looking at the world that allows us to see the invisible frameworks holding it all together.
Okay, so let's start there. Let's put on our scientific lens. The source material opens with a section on how scientists actually work. And I think for a lot of people, maybe they haven't thought about this since, high school chemistry.
Probably.
We tend to think science is just knowing stuff.
And that is the biggest misconception out there. Science is a verb. It's a process. It is a thing you do. The text is very specific about this workflow. It calls it a logical way of working. And it doesn't start with facts. It starts with a guess.
A guess? That doesn't sound very scientific.
What's a guess dressed up in a suit?
Yeah.
We call it a theory or a hypothesis. You observe something happening in the world, maybe the sky is blue, or a rock falls down, and you write down a thought, I think X happens because of Y. That's step one.
But you can't stop there. I mean, otherwise it's just philosophy or an opinion.
Exactly. If you stop there, you just have a debate at a dinner party. To do science, you have to move to step two, the experiment. You have to actively test that theory. You have to measure, observe, and crucially, you have to look for results that prove you wrong.
That is such an important distinction. You aren't just looking for things that agree with you. You're not looking for confirmation bias.
No. In fact, the most valuable result is often the one that contradicts you, because that forces you to refine the theory. It's a cycle of guess, test, check, repeat. And the source highlights some of the absolute titans who refine this process. We have to talk about Isaac Newton.
Yeah.
The 1660s.
The man, the myth, the apple.
The apple. We all know the story. And it might even be true.
But let's unpack that story because I think it gets trivialized a lot. The text points out something about his theory of gravity that I think gets overlooked. It isn't just that things fall.
Yeah.
Any toddler knows things fall. You don't need to be a genius to know that if you drop a cup, it breaks.
Right. Newton's insight wasn't that gravity exists. It was how it behaves. He realized it's an accelerating force. The text uses this specific phrasing. Gravity makes the apple fall faster and faster.
Okay, so it's a pulling force that grabs you. But what was the real leap?
The real leap, the thing that changed the entire world, was universality.
Universality. What do you mean by that?
Before Newton, people honestly believed the rules on Earth were different from the rules in the heavens. Earth was heavy and corrupt, base. The heavens, the moon, the planets, the stars, they were light and perfect and moved in perfect circles.
They're made of different stuff.
Exactly. Two separate rule books. Newton looked at the apple falling, and then he looked up at the moon. And he had this incredible thought. What if it's the same force? What if the same thing pulling the apple to the ground is the thing grabbing the moon and keeping it from flying off into space?
So he unified the sky and the ground. He wrote one set of rules for everything.
Exactly. He wrote the rule book for motion. One law of gravity for apples and for planets. That was revolutionary.
But then you jump forward a few centuries to the other name on the list, Albert Einstein, 1879 to 1955. The text calls him the most famous scientist of all time.
Hard to argue with that. Or the hair.
The hair definitely helps the brand, but his contribution was different, wasn't it? Newton was looking at physical objects, apples, planets. Einstein was looking at the fabric of reality itself.
He was. He was using math to look at the invisible structure of the universe. He was famous for his thought experiments. Instead of a lab, he would sit in his chair and think, what would happen if I were riding on a beam of light?
Which is just a wild question to even ask.
It is. But from questions like that, he wrote down theories about how the universe is constructed. Space, time, light, gravity. Newton explained how objects move through space. Einstein explained what the space they are moving on is actually made of.
And he showed that Newton's rules weren't wrong, just incomplete. They worked for apples and planets, but not for things that are very, very fast or very, very massive.
Precisely. Einstein provided the high-performance upgrade to Newton's physics.
And speaking of seeing the invisible, the source mentions William Röntgen. This is a favorite of mine because it feels like actual magic. X-rays.
It really is a superpower, isn't it? Think about the context of the time. This is the late 1800s. Before Röntgen, if you wanted to see inside a human body, to see a broken bone or a bullet,
You had to cut the person open.
which is usually fatal, or at least very, very unpleasant.
A bit of an understatement, yeah.
Röntgen discovered these mysterious rays that could pass through soft tissue but were blocked by denser materials like bone or metal. He took the first X-ray image of his wife's hand. You could see her wedding ring.
Imagine seeing that for the first time, seeing the bones inside a living person without a drop of blood.
It must have been terrifying and miraculous. It revolutionized medicine overnight. It's a perfect example of how a tool extends our observation. We couldn't see the bone with our eyes, so we built a machine that could.
And we do the same thing for the very small. The text breaks down the fundamental building blocks of matter. We're back to solids, liquids, and gases.
The states of matter. The absolute basics.
I love the simplicity of the definitions here, but I want to push on why they're different. A solid keeps its shape. A rock is a rock. It doesn't care what container you put it in. Why? What's happening at the atomic level?
It comes down to the invisible bonds between atoms.
Hmm.
In a solid, the atoms are locked in a rigid grid, a crystalline structure. They're vibrating, sure, everything vibrates, but they're essentially handcuffed to their neighbors. They can't wander off.
Okay, so they're in a very orderly, very strict formation.
Very strict. Think of soldiers standing in formation.
Then liquids. They flow downwards. They're submissive to gravity. They take the shape of the bottom of the container. So what happened to the handcuffs?
In a liquid, those handcuffs are broken. The atoms are still holding hands, you could say. They're still attracted to each other, but they can slide past each other.
So the formation is broken up.
Exactly. The soldiers can mingle now. They have volume. They stay together. But they lose their fixed structure. That's why you can pour water.
And then gases. This is the one I think is most poetic. The text says gas expands to fill the entire container. It wants to be everywhere.
High kinetic energy. In a gas, the atoms have completely let go of each other. They're bouncing off the walls, moving at incredible speeds. They aren't just mingling. They're in a full-on mosh pit. They want to escape.
And to see this, really see it on a biological level, we need the microscope. The source has this incredible image of blood cells. You look at your hand, it just looks like skin. You put a drop of blood under a slide, and suddenly it's a busy highway.
It's a bustling city.
Yep.
It's a whole universe in a single drop. You have the red blood cells, which are like little delivery trucks. The text is they're the couriers delivering oxygen.
Okay.
Then you have the white blood cells, which are the security guards, the police force, fighting off invaders like bacteria and viruses.
And you'd never know any of that was happening without that tool, without the microscope.
Never. That shift in perspective from the me scale to the cell scale is fundamentally what science gives us. It changes the resolution of the world.
Okay, so we've looked at the microscopic rules. We've established the laws of physics and matter. Now, let's zoom out. Way, way out. I want to look at the stage where all of this drama happens. Planet Earth.
The blue marble.
The source makes a really interesting distinction right off the bat between a globe and a map. And it isn't just that one is round and one is flat.
No, it's about truth versus convenience.
Mm-hmm.
A globe is the truth. The Earth is a sphere, well, an oblate spheroid. Technically, it bulges at the equator, but for
Hmm.
our purposes, it's a ball.
Right.
A map is a compromise. To make a map, to
Yeah.
flatten that orange peel onto a table without it ripping or distorting, you have to make choices. You have to stretch some parts and shrink others.
And that's why Greenland looks the size of Africa on some maps, right? Even though Africa is, what, 14 times bigger?
Exactly. That's the Mercator projection. It was designed for sailors because it keeps the lines of longitude straight, which is great for navigation.
Hmm.
But the cost is that it massively distorts the size of things near the poles.
So the map is a useful lie, but the globe is the reality.
A very useful lie. But yes, a lie nonetheless.
And the reality of that globe, and this is the part that blows my mind every single time I revisit it, is that it is not finished. It's not a static object. We tend to think of the Earth as done. The ground is solid. It's terra firma.
But it's not fixed. It's a slow-motion car crash. Or maybe a slow-motion ballet.
I like that. This is the continental drift section. The text takes us back 200 million years.
200 million years ago. Imagine the map. It doesn't look anything like our map. All the land masses, Africa, America, Antarctica, Europe, Asia, they will all smash together into one giant supercontinent. We call it Pangaea.
A single island and a single ocean.
Correct. The Panthalastic Ocean. And then about 135 million years ago, the engine inside the Earth, the incredible heat from the core, the convection currents, and the molten mantle started to rip it apart.
The breakup.
The Great Divorce. The tectonic plates started drifting. And by 10 million years ago, you'd start to recognize the pieces. You'd see a shape and say, hey, that looks like India. But it would be an island floating in the middle of the ocean, heading north on a collision course with Asia.
And that crash created the Himalayas, the highest mountain range in the world.
Precisely. The mountains are just the crumple zones of that collision. When two massive continental plates hit each other, something has to give. The land has nowhere to go but up. It buckles and folds.
So the takeaway here is that we are all passengers on these gigantic shifting rafts. The ground beneath our feet is moving right now, just too slowly for us to feel it without very sensitive instruments.
We're moving at about the same speed your fingernails grow. We're living on a dynamic, restless planet the map is just a snapshot of right now.
Let's take a tour of these rafts then. The Seven Sisters, the continents. The text gives us a great snapshot of each. Let's run through them, starting with the heavyweight, Asia.
The monster. It's the largest continent by land area and by population by far. But the stat that always stops me in my tracks is the population. It's home to 2/3 of the world's people.
2/3? That's staggering.
It is. If you pick a random human being off the planet, the odds are overwhelmingly in favor of them being in Asia. It is the center of gravity for humanity,
Then we have Africa.
a continent of extremes. The text highlights it as the longest river, the Nile, and the largest desert, the Sahara. It is physically massive and centrally located. It's the only continent that stretches from the northern temperate zone all the way to the southern temperate zone.
So it has an incredible diversity of climates.
Incredible, from Mediterranean coasts to equatorial rainforests to vast deserts and savannas,
North America.
Canada, Mexico, and the USA with its 50 states. Defined by its variety, from the frozen Arctic north of Canada and Alaska through the Great Plains down to the tropical south of Mexico and Florida.
South America. The text mentions the tail specifically.
Yes, it tapers down to that narrow point near Antarctica Tierra del Fuego, the Falkland Islands. It's the fourth largest. And it's really defined by that incredible spine of mountains, the Andes, running down the entire western side of the continent.
Like a backbone.
A geological backbone, exactly.
And the lonely one. Antarctica.
The frozen bottom of the world. A continent of ice. And notice the distinction the source makes. No permanent residents.
It's a continent without citizens.
Exactly. No one is Antarctican. It is a place for science and for peace, governed by an international treaty. It's the only landmass on Earth dedicated entirely to research. It doesn't belong to a country in the traditional sense.
Then Europe.
Small but dense. The text defines it by its political and cultural density. Many different languages, many different cultures, many different countries, all packed into a relatively small area.
A historical patchwork quilt.
A very complex one, yes.
And finally, Australia and Oceania.
The smallest continent. The island continent. Often grouped with New Zealand and the thousands of islands scattered across the Pacific Ocean, which we call Oceania.
But we can't talk about the Earth without talking about the blue stuff. The oceans cover 2/3 of the planet. It's more of a water planet than an Earth planet, really.
It absolutely is. And the source identifies 5 of them. Pacific, Atlantic, Indian, Southern, and Arctic.
The Pacific is just, it's unfathomable, the scale of it.
It covers a third of the Earth's entire surface. Just visualize that. One single body of water is larger than all the land on Earth combined.
Wow.
You could fit all 7 continents inside the Pacific Ocean and still have room to swim.
That is both terrifying and humbling. And the text answers the question every kid asks at the beach. Why is it salty?
It comes back to the rocks. It's essentially rock soup.
Rock soup. I like that. Explain.
Well, basically, rain falls on the land. Rain is naturally slightly acidic because it absorbs carbon dioxide from the air. This slightly acidic rain falls on rocks, and over millions of years, it erodes them. It dissolves the minerals in the rocks. And sodium chloride, table salt, is a very common mineral.
And then it washes into the rivers?
Washes into the rivers, and the rivers carry that entire mineral load to the ocean. Now, here's the crucial part. The sun evaporates the water from the ocean to make rain clouds, but the salt doesn't evaporate. It gets left behind.
So it's a one-way trip for the salt.
It's a one-way trip. So over millions and millions of years, the ocean just gets saltier and saltier. It's the ultimate dumping ground for the land's minerals.
And it's moving, too. It isn't a bathtub. It's not static.
Oh, constantly. The source mentions 3 types of movement. You have currents, which are like vast rivers within the sea, moving huge amounts of warm or cold water around the globe. You have waves, which are mostly driven by wind blowing over the surface. And you have tides, which are driven by the gravitational pull of the moon and the sun.
It's a churning, living engine that distributes heat around the planet and drives our weather.
It's the planet's circulatory system.
Okay, speaking of engines and extremes, I want to play a little game. The source material is absolutely packed with world records. The highest, the driest, the hottest. I'm going to throw a category at you, and I want you to give me the location, but more importantly, I want you to give me the context. Why is it there? You ready?
I was born ready. Let's do the Earth's superlatives.
All right, let's start at the top. Highest place on Earth.
That has to be Mount Everest. Located in the Himalayas in Asia, 8,848 meters, or 29,029 feet. It's literally the cruising altitude of a 747 jet.
And going back to our earlier point, why is it so high? Why there?
Because of that continental collision we talked about, the Indian subcontinent is smashing into the Eurasian plate. The land has nowhere to go but up. And the crazy part is, it's still growing, just by a few millimeters a year, but it's still rising.
Unbelievable. Okay, longest river.
The Nile, in Africa. Though we'll note there's a fierce debate among geographers about whether the Amazon might actually be slightly longer, depending on where you measure from. But our source lists the Nile, so we stick with the Nile.
And what's its significance?
It's the lifeblood of that region. It snakes its way north through the desert. And for millennia, ancient Egypt was entirely dependent on its predictable annual floods to deposit fertile silt for farming. It's a river that birthed a civilization.
Largest lake.
By surface area, that's Lake Superior in North America, one of the Great Lakes. It holds 10% of the entire world's surface fresh water. It's basically an inland freshwater sea. It's so large it creates its own weather systems called lake effect snow.
Okay, let's turn up the thermostat. Hottest place on Earth.
The source name's Delol, Ethiopia. It has the highest average annual temperature for an inhabited place.
I looked at pictures of this place. It does not look like it belongs on Earth.
No, it looks like Io, one of Jupiter's moons. It's a volcanic landscape in the Danakil Depression. You have these incredible yellow and green pools of acid, sulfur springs, and salt formations. It's incredibly hot, not just because of the sun, but because the heat is coming from below, too. It's geologically active.
Now, flip the switch. Coldest place.
The pole of inaccessibility, Antarctica.
That name, the pole of inaccessibility. It sounds like something from a fantasy novel. It's so evocative.
It is, and it's a geographic term. It's the point on the Antarctic continent that is furthest from any ocean in any direction. It's the geometric center of the ice.
And why is that the coldest?
Because it's devastatingly cold for 2 reasons. 1, high altitude on the polar plateau, and 2, the ocean, which usually acts as a massive heat sink and moderates temperature, is as far away as it can possibly be. There's no warming influence.
And windiest. This one surprised me.
Also Antarctica, Commonwealth Bay. The wind speeds there can regularly exceed hurricane force. It's caused by what are called katabatic winds.
Katabatic winds.
Cold, dense air forms over the high polar plateau. Gravity pulls this heavy air down the steep slopes towards the coast, and it accelerates as it goes. It's essentially a permanent avalanche of air.
Okay, here's a contrast that I think really illustrates how geography works as a system. The rainiest place versus the driest place.
Okay, the rainiest is Mount Waialae in Hawaii, on the island of Kauai.
It sounds like a shower that just never turns off.
That's a good way to put it. It rains almost every single day. And the reason is simple geography. It's a tall, conical mountain that stands right in the path of the moisture-laden trade winds coming off the Pacific.
So it's an obstacle.
A perfect obstacle. The warm, wet air hits the mountain, is forced to rise up the slope. It cools down as it rises, and cool air can't hold as much moisture, so it just dumps its water as rain. It's a rain-making machine.
And now for the opposite, the driest place.
The Atacama Desert in Chile, South America.
This is the one that shocks me. Because Chile has a huge coastline, it is right next to the massive Pacific Ocean. How can a place next to all that water be the driest place on Earth?
It is a cruel trick of geography. The Atacama is caught in a double rain shadow. To the east, you have the massive Andes Mountains, which block any moisture coming from the Amazon basin.
Okay, that makes sense. But what about the ocean to the west?
Well, off the coast of Chile runs the Humboldt Current, which brings very cold water up from Antarctica. Cold water doesn't evaporate very well, so you have this huge body of water that produces very little moisture, creating coastal fog, but almost no rain clouds.
So you are sandwiched between giant mountains and a cold, unhelpful ocean.
Exactly. There are parts of the Atacama where it has literally never rained in recorded human history. It's a desert created by a perfect storm of geographical bad luck.
So you have Hawaii drowning in water and the Atacama gasping for a single drop, all because of how the mountains and the ocean currents interact.
Exactly. It shows that climate isn't random. It is a machine with predictable inputs and outputs.
So let's stay in those harsh zones. We talked about the Atacama, but the text goes deep into the desert biome in general. It calls them seas of sand.
It's a poetic description, but for the people and animals living there, it's a challenging reality. Specifically in places like the Namib Desert in Africa. The wind blows the sand into these absolutely massive dunes, some of them 200 meters high.
That is a skyscraper made of sand.
A skyscraper that moves. The text mentions that dunes creep. They migrate with the wind. The wind blows sand up the shallow side and it cascades down the steep side. Over a year, a whole dune can move several meters.
And they can swallow things.
They can. They can bury entire villages, roads, anything that gets in their way. It's a landscape that is constantly reshaping itself.
And it isn't just sand, right? The text talks about the rock formations, buttes, like in Monument Valley in the American Southwest.
The mitten rocks, those iconic shapes. That's wind erosion. The wind picks up sand and tiny bits of rock and uses it like sandpaper, blasting away at the softer rock for millions of years. The buttes are what's left, the harder, more resistant rock that survived the sandblasting.
But life finds a way. Even in this sandpaper factory, something grows.
It does, but it has to adapt. It can't play by the normal rules of plants. Look at the saguaro cactus, the classic cartoon cactus with its arms up. Yeah. It's a masterpiece of engineering. First, it has no leaves. Leaves have a huge surface area and would lose too much water through evaporation in the hot sun. Instead, it has spines for protection from animals that want its water.
And the stem is like a water barrel.
Exactly. It is a pleated accordion-like stem that can expand to hold huge amounts of water after a rare rainstorm. It drinks deep when it rains and then hoards that water for months. And its roots are shallow but spread out wide to catch any surface water. It's a survivalist.
And the animals. The camel, the ship of the desert. The text mentions caravans in the Taklamakan Desert in China. The camel is a biological marvel.
It really is. The hump isn't for water, it's for storing fat, which is concentrated energy. It can go days without water because its body is so efficient at conserving it. It has wide, splayed feet so it doesn't sink in the soft sand. It has long eyelashes and nostrils that can close to keep the sand out of its eyes and nose during sandstorms.
It is perfectly engineered for its environment.
Every feature is a solution to a problem posed by the desert.
And people, too. The text talks about nomads.
People like the Bedouin or the Tuareg. They live in tents, they move for food and water. They don't fight the desert, they flow with it. Their culture is defined by mobility. If the resources move, you move.
And at the center of that life is the oasis, the magic spot where water seeps up from underground aquifers.
Life in the desert is entirely defined by the distance to the next drink of water. An oasis isn't just a place, it's the center of the universe.
Now, there's another biome the text covers that's sort of the middle child. It isn't a lush forest, but it isn't a dead desert. The grasslands.
The dusty plains. The source defines them as places too dry for forests to grow in large numbers, but just wet enough for grass to thrive.
I love how the text breaks down the regional names for this, because it's the same basic ecosystem, but we brand it differently depending on where we are in the world,
Right. If you're in North America, you're on the prairie.
which is now the breadbasket of the world.
Exactly. We
Yeah.
plowed up most of the native tallgrass prairie and planted wheat, which is, at the end of the day, just a type of grass that we can eat. But originally, it was an ocean of grass, home to millions of bison.
In South America.
It's the pampas. And the wildlife there is eccentric. The text specifically mentions the giant anteater.
I looked up a video of a giant anteater after reading this. It looks like a mistake. It has like a vacuum cleaner hose and this huge bushy tail it carries like a flag.
Evolution has a sense of humor,
Mm-hmm.
and the pampas also has vizcachas, which are these social burrowing rodents that look a bit like rabbits with long tails, and rayas, which are large flightless birds similar to ostriches.
And then, of course, the most famous grassland of all, Africa.
The savanna. This is the classic wildlife documentary setting we all picture.
The food chain is so visible there, it's completely undisguised. There's nowhere to hide.
There really isn't. You have these massive herds of grazers, zebras, impalas, wildebeest, elephants, giraffes. They're all there for the grass, the primary producer.
And because the meat is there?
The predators and the scavengers are there. Lions, cheetahs, hyenas. And the text mentions vultures, circling high above, soaring on thermals, waiting to swoop on any scraps left behind. It's a brutal, efficient cycle.
And just like the desert, it's all driven by water.
Absolutely. The Great Migration of the wildebeest across the Serengeti is just a giant, continuous search for rain and the fresh grass that follows it. They're following the water.
It really highlights that life is dictated by the environment. If you live in a place that's flat and grassy, you learn to run fast. If you live in a place that's dry, you learn to store water or to move.
Adaptation is the key to everything.
Okay, speaking of learning to adapt, I want to zoom in now. We've looked at the continents, we've looked at the deserts and grasslands. Now I want to look at a type of creature that seems to be stuck between worlds. The amphibian.
The double life. That is literally what the word means. Amphi means both. Bios means life.
The text spotlights frogs, toads, newts, and salamanders. And the key rule for all of them is you can visit the land, but you can never fully leave the water.
They are the bridge. Evolutionarily speaking, they were the first vertebrates to step out of the water and onto land. But they didn't cut the cord. They still have to go back to the water to lay their eggs, because their eggs have no shell and would dry out on land.
And their skin too, right?
Exactly. Their skin is permeable. They can actually breathe through it, but that also means it dries out very easily. They have to stay moist.
Let's settle a debate right now that I'm sure keeps our listeners up at night. What is the actual definitive difference between a frog and a toad?
The text gives us a handy identification guide,
Yep.
generally speaking. Frogs tend to have smooth, moist skin and long, powerful back legs built for leaping.
Okay.
Toads, on the other hand, tend to have dry, bumpy, warty skin and shorter, stubbier legs built for crawling or short hops.
So if it's slimy and jumps into the next county, it's a frog. If it looks like a grumpy pickle and waddles away, it's a toad.
That's the non-scientific heuristic, but it works pretty well. And toads often have that patterned, earthy-colored skin for camouflage to hide in the dirt and leaf litter.
The life cycle here is just bonkers when you really think about it. We take it for granted because we learned it in kindergarten, but imagine if a human did this. Imagine if you were born as a fish, and then a few weeks later, you turn into a person.
It is extreme metamorphosis.
Mm-hmm.
It's one of the most dramatic transformations in the animal kingdom. You start as frog spawn, these jelly-like clumps of tiny black eggs laid in water.
Right.
Then you hatch into a tadpole. At this stage, you have gills. You have a tail. You are, for all intents and purposes, a fish. You swim, you eat algae.
And then the magic happens.
The magic happens. The back legs sprout out first, then the front ones. The tail starts to shrink and is actually absorbed back into the body for nutrients. Internally, lungs develop so you can breathe air. The whole digestive system changes from an herbivore's to a carnivore's.
And suddenly, in just a few weeks, you're a tiny baby frog leaving the pond to walk on land. It's a complete biological reinvention.
It's two different animals in one lifetime.
And once they're on land, they have some serious superpowers. The source material highlights a few.
Oh, absolutely. Let's talk about the jump.
The African sharp-nosed frog.
This thing is an Olympian. It can jump 5 meters. That's about 16 feet in a single hop.
That's like me jumping over a 2-story house. It doesn't seem physically possible.
It's the equivalent of a human jumping nearly the length of a football pitch. The physics of those leg muscles are incredible. The tendons in their legs act like catapults. They stretch and store elastic energy and then release it all in an explosive burst.
And then you have the tree frogs. They went a different route. Not long, but vertical.
Sticky toes. They didn't develop power, they developed grip. They have specialized pads on their fingers and toes that are covered in microscopic structures that allow them to cling to surfaces like glass.
And the text points out their eyes. They're forward-facing. Why does that matter?
Depth perception. If you're an animal that jumps from branch to branch high in the forest canopy, you absolutely cannot afford to miss. You need binocular vision with both eyes pointing forward to judge distance perfectly.
And let's not forget the tongue. The classic cartoon, ZAP.
It's a projectile weapon. It's incredibly fast, sticky, and elastic. It's attached at the front of the mouth, not the back, so it can flick out further and faster to catch insects, usually at night.
But not all amphibians are friendly little hoppers. Some of them are walking chemical weapons factories.
The poison dart frog from the Amazon, those incredibly bright colors, electric blue, vivid yellow, fiery orange. In nature, bright colors are usually a neon sign that says, "Do not eat me."
It's a warning label.
It is. It's called aposematism. It's a strategy that signals to predators, "I am toxic, you will regret this." And their toxins are some of the most potent in the world.
And newts do this too.
Many newts and salamanders do. They have brightly colored bellies, orange or red, that they flash when threatened. Same message. I taste terrible and I might kill you.
And then there's the oddball, the Sicilian.
The one that breaks all the rules. It looks like a giant worm or a small snake. It has no legs.
But it is an amphibian.
It is. It has the same moist, permeable skin, and it goes through a similar life cycle. It just decided, evolutionarily speaking, that legs were getting in the way of its burrowing lifestyle, so over millions of years, it got rid of them. The text says it uses its strong, bony head as a shovel to dig through the mud and soil.
It is amazing to think that on the same planet, you have a camel perfectly adapted to walking across a sand dune and a Sicilian perfectly adapted to digging through mud with its head.
Both are just adapting to the specific stage the Earth provided for them.
And that is the beauty of it. The stage, the geography, the climate sets the challenge. Life provides the solution. So we have covered the natural world. We have covered the physics that shape it. But there is one more layer we have to add. The layer that we, humans, painted on top of it. The human map.
Political geography.
The text makes a really important distinction between natural borders, like rivers, oceans, and mountains, and political borders.
Natural borders make intuitive sense. A river is a barrier. A mountain range stops you. It's easy to say, I'll stay on this side, you stay on that side. Political borders are imaginary lines we draw on a map and then agree to respect. Or, more often than not, fight over.
And inside those lines, we have countries. The source says there are over 190 of them worldwide.
Each with its own leaders, its own laws, and usually capital city.
Which is defined as simply where the government meets. The text gives examples like Buenos Aires for Argentina or Moscow for Russia.
And the size difference between these countries is just comical. The text compares the giant to the tiny.
The giant being Russia.
17 million square kilometers. It stretches across Europe and Asia. It's so big it spans 11 time zones. When people in Western Russia are eating breakfast, people in Eastern Russia are going to bed.
And the tiny
Vatican City, located entirely inside the city of Rome, in Italy.
It is a country inside a city. It's hard to wrap your head around.
It has a population of about 1,000 people. It is the smallest independent state in the world. You could walk across it in a few minutes. To cross Russia would take you months.
And how do we know all this? How do we draw these lines? Mapping technology. We talked about the globe versus the map earlier, but the text mentions the evolution from hand-drawn maps to what we have now.
It's been a massive evolution, from ancient cartographers trying to sketch the coastline from a ship to the age of exploration to now, where we have airplanes and satellites feeding digital information to powerful computers.
We've moved from artists' interpretations to digital precision.
We have. We use grids, letters, and numbers, or more precisely latitude and longitude, to pinpoint exact locations on the planet's surface.
And the atlas, the book of maps. It's funny, the source mentions atlases, and it feels almost nostalgic now that we all have GPS in our pockets. But there's something about opening a big book and seeing the whole world laid out.
It gives you that context, again, that sense of scale. When you look at an atlas, you see the relationships between places. You see how Russia sits above China. You see how close Africa is to Europe at the Strait of Gibraltar. You lose that big picture when you just type an address into a phone and see a blue line.
So we have traveled from the theory of gravity to the frog's incredible jump. We have gone from the center of the atom to the center of the Antarctic continent.
It has been quite a trip through scale.
If you had to boil this entire deep dive down, this theory of everything episode, what is the headline for you? What's the main takeaway?
For me, it's the undeniable connection between the physical laws and the living reality. We started with physics. Gravity pulls the water down to make the oceans. It holds the atmosphere in place. The tilt of the earth and the heat from the sun create the deserts and the ice caps. And then biology, the frogs, the cacti, the camels, the humans. We are all just finding clever ways to fit into the niches that physics and geography created for us.
We are the tenants of the building that physics built.
That's a great way to put it. And the building is constantly undergoing renovations.
That brings me to the final thought I wanted to leave our listeners with. We talked about continental drift. We know that 200 million years ago, the map was one giant blob, Pangaea. We know that today it's the scattered continents we recognize.
And we know for a fact that they are still moving.
Right now. So here's the question. If we could jump in a time machine and look at a map of Earth 10 million years from now, would we even recognize our home?
Probably not. The Atlantic Ocean might be much wider. Africa might have finally split apart at the Great Rift Valley, creating a new ocean. California might be an island sliding north towards Alaska.
And if the map is different, imagine the creatures. The whole stage has been rearranged. What kind of new amphibians will be jumping around in the new jungles of a shifted continent? What new deserts will create new, even more efficient camels?
It's a fascinating thought. The story of life on Earth isn't over. We're just in the middle of the book. Evolution is still writing new chapters.
You're just reading the current page.
Exactly.
Well, on that note, we're going to wrap up this journey. We hope this gave you a new perspective on the ground beneath your feet and the air in your lungs.
Keep looking closely. Whether it's at a map in an old atlas or just a bug in your garden, there's always more to see.
Thanks for listening. Until the next deep dive, stay curious.